Hello! Today it's the project that I'm going to introduce. So what we're going to do in this video is go through what the project is in Advanced Integrated Circuits that I'm teaching now in a few weeks, and what you are going to do. And let's dive in. So I wanted to start with a quote from last year. So this is, I asked Domin, one of the students from last year, for a quote, and he said, "A fantastic project that might just turn your world upside down, push you to re-evaluate your life choices and stare briefly into the existential void, all while being deeply enjoyable and engaging." And I really like this comment. The reason I like it is that it is a hard project. It will be tough. It will be hard. And the reason I made it like that is that I want you to learn. And I do believe that one of the ways to ensure that you actually learn something is to force you into an environment where you just have to learn. And that is the purpose of the project. Last year, 2 groups actually got all the way to tape out. So we taped out on the, was it the, let's see what the shuttle was. Yeah, TT-Sky25A. That's where we taped out. So if you go here and you go to Janeway temp, you'll see my name, but it's really the students' work. So you'll see the description from the students of their temperature sensors. So it should be really interesting to see when it comes back. First of all, whether they start up and whether we were able to measure temperature with these temperature sensors. So that's going to be really cool. So that's what you're going to do this year also. So your challenge is to design a temperature sensor. And you're going to do this in groups. I'm going to force you into groups. You will not have a choice. You will have to work together. Now, one of the reasons I want you to design a temperature sensor is that it is a quite common sensor that we need in integrated circuits. What you're seeing on the screen right now is an example of a regulator systems. I believe this is the 54L15 from Nordic Semiconductor from their product description. You can see the external voltage VDD, which is connected to usually battery, like a coin cell or something like that. And then there's a box here called VReg main. And inside there we can see 2 names, DC-DC. So that's a DC-DC converter, usually a buck, because we can see the external inductor here. And there's an LDO inside. And we can see that the buck actually powers the digital supply, which is connected to the analog supply, which is powered by the LDO. And then we have the RF supply. So if you don't know, microcontrollers like these have, well, they spend most of the time in system off, or they're not operating at all. All they're doing is maintaining the voltages and keeping things in sleep, going into the lowest possible power state. And once in a while, they wake up. And in this case, it has a radio inside, and this is a Bluetooth chip. So it will transmit a few packets, receive a few packets, see what it should be next. And then if it shouldn't do anything, it'll go back to sleep. This leads to a very dynamic current consumption. So the current consumption can go from nanoamps to tens, maybe 100 milliamps relatively quickly. Now, we were able to handle that quite efficiently in these type of circuits by not using the same regulator all the time. The system will sort of switch. Now I'm going to turn on the radio. Okay, so I need to switch to the high power regulator, and sort of do this dance of powering the whole system and ensure that the supply stays within bounds. But it's quite tricky to do. One of the things that makes it even more tricky is that leakage current in digital sections. So much of these chips have digital circuits, like millions of gates. And even if you turn them on, if you turn them off, if you don't have clocks running, but they're actually on, as in they're powered, but they're not doing anything, they are leaking. They're leaking quite a bit. And that leakage current, that is, well, it's driven by quantum mechanics. So it's basically driven by what's the built-in voltage between the source and the, well, underneath the transistor gate. Now, this actual voltage underneath the transistor gate is called the surface potential. I keep getting confused with the names, but this depends on the threshold voltage. That's this VT here. So it has sort of an exponential relationship with the threshold voltage. Is there a... Yeah, no, this is sort of the leakage current, yeah, because we have, if we reduce the threshold voltage, then the leakage current will increase. In this case, it actually doesn't take into account the fact that you can change the gate voltage of the transistor also to increase the current, of course. But now we turn it off. We've connected the gate to source, and it's supposed to be completely off. But the MOSFET isn't completely off. It has this dependency on the threshold voltage. And when we scale down into nanoscale technologies, this threshold voltage will usually, well, it will be lowered, but there's a limit to how much you can lower it, because if you lower it too much, then this leakage current increases exponentially. So when we look at how this leakage current behave, we can actually just take two NMOSes. This is two NFETs. And we can see the bottom one, that's a standard transistor, sort of standard 1.8 volt transistor. The top one is a low threshold voltage. And we can see here for the red curve and the green curve, there is like a couple of orders of magnitude, or maybe an order of magnitude difference in the leakage current. And that's quite a lot. But not only that, we can see that over temperature, so the x-axis here is temperature. Over temperature from 0 degrees to 150 degrees, we're going like a couple of orders of magnitude, no, many orders of magnitude, from 10 femtofarads to 100 picofarads. So the leakage current of MOSFETs has this huge temperature dependence. And that complicates our system, because let's assume now that we're actually not doing something right now in the chip, but we might do something in the next couple of microseconds, maybe in 10 microseconds. So the time's too short to turn off the full system. Okay? But we still want the absolute possible lowest power consumption. So we've stopped all the clocks and we're sort of ready to do something. But now, what is the current consumption? Because let's assume that at 25C, in this case, we have 100 million logic cells. So at 25C, we have about 100 microamps. At 125C, we're up to 100 milliamps. Now, if we're not doing something, and the current is usually in the 100 microamp range, then we don't need the biggest regulator to control the system. But I promise you, if we're consuming 100 milliamps, you'll probably need the biggest regulator in the system. So unless the microcontroller or the system has some knowledge of temperature, you're left with sort of analog solutions to this efficiency problem. And designing something that sort of spans this multiple orders of magnitude is tricky. So, because in this low dropout regulator, it's fine to use 1 microamp at 25C. That's about 1% of the budget. That's fine. That's quite efficient. But if you use 1 milliamp, well, then you're sort of 10x the leakage current. So that doesn't make sense. So at 125C, you can use a lot more for the regulator, but you don't know what the temperature is. So you could design that into the regulator, make it temperature aware. But what if we can just make a temperature sensor? What if we can make a temperature sensor that we can actually scatter around the chip? Because it's not always the case that the temperature is the same across a chip. If you have a huge chip with a lot of cores or power amplifiers or things that consume a lot of current, like an LDO, the temperature locally might be quite high. Significantly higher than one end of the chip might be higher than the other end of the chip. So it would be good to know temperature. So that's the problem. We want to know what the temperature is on the die, on the chip. Okay, So now we need to design a temperature sensor. You probably have no idea how to do that. But that is what I'm gonna help you learn across this semester. And it is a rather complicated system. You're looking at it on the screen right now. So what we'll start with is to make a circuit that's called a bandgap that generates a current that is proportional to absolute temperature and a voltage that is inversely proportional to absolute temperature. So both of the current and the voltage here is actually a function of the temperature. Now we can take that current and that voltage and we can put it into an oscillator where we can generate a frequency that is dependent on those two components, the current and the voltage. And now we have a frequency that is dependent on temperature. Now, a frequency we can actually measure usually on the chip, because quite often we'll have low frequency clocks we'll have high frequency clocks also. If the radio is running, we'll have a high frequency clock available, accurate one. But even when the radio is not running, we could have a low frequency clock that is accurate. In most cases, it will be a 32768 Hertz oscillator or clock frequency. And quite often, well, not always, but sometimes it comes from a crystal. Actually, there's a good video. I should link that in. If we jump to the lecture notes, I'll put the lecture notes for this lecture. I've put that on AIC26, so you might not be able to see that, but it says AIC26, the project. I'll put it in the notes below. I think I added a link here to a good video on the oscillator. Didn't I? Or did I do it in my imagination? Okay. If you go to Analogicus and get to the course page, and we'll have a look at the videos. I do think I added to the course videos. Yeah, here it is. There's a video by Steve Mould that shows you how the crystal oscillators work and why it's actually 32768 Hertz. So when we have a reference frequency, we can actually measure a other frequency. We can do that by counting how many clock cycles do we have on the high frequency. So this FOSC will be high frequency in a certain duration of the 32 kilohertz clock. So we can just put this high frequency into a counter. We can count how many what the count is, and the count will be then proportional to temperature. We can then back calculate through knowing how this relaxation oscillator works, and through the bandgap, how that works, how the current and the voltage relate to temperature, how the frequency relates to temperature. We can back calculate what the temperature must have been given the count that we have now. And this is what you're going to do. Now, if you're sitting there now and you're thinking, I have no idea how to do this, then you're probably correct. But don't worry, we're going to break it up. I found that it helps a bit if we break it up into pieces. It's like that, I don't know if it applies in English, but it's the how do you eat an elephant one piece at a time and make sure the pieces are small enough. So what we're going to do is break it up into milestones. Milestone 1, that is to design this bandgap circuit. So that contains an op-amp. It contains, well, I'll teach you about them and about the circuits. Actually, if you want to get a preview, you can go to the course page, you can go to the project, and if we scroll down to milestone 1, you can also find the link to the course page on a bandgap and how those work. There's even a video. So these milestones, I try to make sure that the lectures sort of fit to the milestones. But if you want to get started before that, you can watch the lecture, you can try to read about it in the book, you can get up to speed on the bandgap, and you can start your design. But I'll talk a bit more about the milestones soon. Milestone 2 will be the relaxation oscillator, turning the current and the voltage into a frequency. And the last milestone, not the last milestone, but the last design milestone will be to turn this frequency into a digital value that we can actually say, okay, given this digital value, the temperature will be Y. After that, there comes an optional milestone. And I've made it optional because I've seen in the previous years that not everybody has the skill or the interest or whatever to get through to doing what we call the physical design, to actually doing the layout and getting ready to tape out. So that's optional, but it does count towards the grade though, and we'll look at that later. Then you'll write a report, and this report will be individual. You have to hand in an individual report. I force you to work in groups, which means you might be in a group with somebody you are not happy with, or that you don't feel contribute, or insert whatever you have feelings about here. And the individual report is my way of making sure that the grading on the project is going to be fair. Your contribution is going to be valued. But you need to work in a team because it's a lot of work in this oscillator, designing this system. So it's really good not to do it alone. It's incredibly difficult to do it alone. Now, if your group reaches all the way to the finished layout and milestone 4 is submitted, then there's also an opportunity to get to what we call a tapeout, where we actually send via a tiny tapeout your temperature sensor to manufacturing. And a year later, I think it's a year later, usually it's a year later. Let's have a look at the tiny tapeout schedule. Where did it go? Yeah, tiny tapeout. So let's see, tiny tapeout ships. So the upcoming milestones, so that's TT Sky 26B. That's the targeted one. Estimating shipping December. Yeah, so okay. So not that long actually. That's pretty good. So that'd be cool, huh? If you're actually able to tape out. Now, if you're at NTNU and if you're in my course, then I've got Nordic Semiconductors to sponsor the tape out, which means that you get it for free if you get all the way to the end. If you don't get all the way to the end, well, too bad. That's life. If you're not at NTNU, then you can still tape out. I just won't pay for it, but you can pay yourself. And that would be really cool. So, in order to try and constrain the design, I've made a specification. And this specification is intended to fit into roughly the problem description I talked about earlier, measuring the temperature on the chip in multiple locations. So the area should be rather small. We want the conversion time, so how long does it take to measure a temperature, to be quite short, because we want the system temperature sensor to wake up, take the temperature, go down. Now, temperature doesn't change that fast, but the longer you keep the temperature sensor on, the more current it will consume. So we don't need to sample that often. I think probably for most systems, 100 millisecond intervals is more than enough. So usually temperature in the world changes on the order of seconds, not microseconds. So of course, if you have a ginormous RF power amplifier sitting on your chip, the temperature might change very fast when you turn it on. But we're still talking like milliseconds probably. The leakage current in your system should be really low. You shouldn't consume any current. And that's quite important because when a system is off, you shouldn't really consume current. That's wasted current. The active current should be less than 100 microamps. And the average current, well, if we sample once every 100 millisecond, and the conversion time is 30 microseconds, then we can take the active current, multiply that by the conversion time to get actually charge. and then divide that by the sample rate, which is 100 milliseconds, to get back to like average current over that interval. And then we can add the leakage current. And that gives us a good measure of the sort of performance of the temperature sensor. So for this type of application, we don't actually need fantastically high accurate temperature sensors. So plus minus 10 degrees for 0 to 70 with one temperature calibration. So here it is okay to calibrate once in production. So we have to test every single chip we make. So in production, we can actually test. If we know the temperature in production, we can calibrate to that temperature and blah, blah, blah. So it's fine to do one trim or 1-point trim. You can also do 2 temperature trim, but then usually that's a bit more expensive because you have to have two tests of your chip in production, and that add cost, at least double the cost. Now, grade. For the project, even the early milestones count towards the final grade, and this is really important. There is a milestone that starts the first week, so next week, and that is milestone 0. You have to do that, and that is to complete a tutorial. Again, I'll go a bit more into the description of the milestones. So for the milestone 0, you can get 5 points. And if you don't hand in milestone 0, you will not get the 5 points, and you will have lost out. So you'll get less points on the final grade. Same for milestone 1, 5 points, milestone 2, 10 points, milestone 3, 10 points, and milestone 4, the layout of your circuit, that's 20 points. And now we get to the report. The report is maximum 48 points. And then I have call it a, because I want to, coolness factor, whatever I want to choose to put into that I might award to a person or a group. Or previous years I've had different criteria. I'm not going to put the criteria anywhere. This is going to be my flexibility. But previous years I've had individual contribution as one of the points. In total, you can get 108 points. Now, actually, the grade stops at 100. So I think the A is from 89 to 100 points for the project, which means that there's actually more points than you get. It's not normalized, the grade scale from F to A, or based on these 108 points. It actually maxes out at 100. But that's just building in a little bit of flexibility. Okay, but it's really important to get started right away with the milestone 0, which is the tutorial. So you will find all the information on Blackboard and things like that for the students of mine. And the tutorial, just do that right away. Get started, because it's a lot of work. And it's a lot of work to get tools installed. It's a lot of work to do that tutorial. If you have all the tools up and running, and if you know what you're doing, it shouldn't take more than an hour, maybe. But if you don't know what you're doing, it's going to take longer. So you have to get started on this. And I promise you that it will teach you sort of how to move around the tools, how to add transistors, how to simulate things. It will teach you the skills that you need to know in order to progress on the project. Once you have the milestone 0, you're going to move on to milestone 1. And the way this is going to work is that every single Friday we're going to get together at 10 o'clock at NTNU. We're going to have, first of all, a check-in where we talk a little bit about our state of mind, just in the group. And then you're going to work on the project together. So the first part will be milestone 1 with the bandgap. What you're looking at on the right side is a example of a bandgap circuit. And I'm not going to... Should I go through the details now? Let's take the principle. So the block here in the middle is an operational transconductance amplifier. All you need to know about op-amps at this stage is that it's a magical instrument that forces the inputs to be the same if you're hooking it up right and if it works right. So what we can know is that the voltage here, VD1, is going to be equal to VR1, or these two voltages will be equal. Now it turns out that if we make a size difference in the diodes here, so this is a 1 to n, usually 1 to 8 or something like that, then it turns out that the voltage across the second diode, that it will actually be lower because it's bigger. So you can work that out from the diode equations. What's not immediately obvious from the diode equations is the temperature coefficient of these two voltages. So I'll just say right now, it's if you work it through, it's not the way you think. It actually goes down with temperature. So if this is this is low temperature, then this is high temperature. So it looks like that. It goes down with temperature. It's what we call complementary to absolute temperature. Okay, so what does that entail? Well, this voltage goes down, this voltage goes down. Now, the trick here is that the difference between VD1 and VD2, yes, both of VD1 and VD2, they decrease with temperature, but the difference actually increases. And you can calculate that from the equations. We'll get back to that in the diode lecture. But that difference actually is proportional to temperature. It's like kT divided by Q times the logarithm of the size difference. So that voltage is known, which means that the current here, the ID, is basically just that voltage difference between the VR1 here and VD2 divided by R. And that's the magic of the band gaps. The reason it's called a band gap is that if you extrapolate these VD1s all the way to absolute zero Kelvin, then you're getting close to the band gap voltage, and it relates to the quantum mechanics of diodes. And we'll look into more of that. So if you actually want to calculate the current in a diode, then you have to go all the way back to Schrödinger. And you have to start there with Schrödinger, and then go forward through density of states, and then forward through the Fermi-Dirac equation, and the mobility, and effective mass, and all the stuff that you have maybe forgotten about from solid-state physics before you get to the temperature coefficient of the diode voltage. But we're going to talk about that in the band gap lectures and in the lectures before that. After you made milestone 1, you're going to move on to milestone 2, which is the oscillator. So here we have a voltage and we have a current. And now we want to turn that into a frequency. So we're going to do that by using a capacitor. One way to do it is to have your current, and that's actually a mistake in this picture I see. I'm missing the diode connection, which is a bit, okay. Diode connection here. And then we have a voltage. Here I'm actually using the current to generate a voltage. This is not a good idea for your temperature sensor, because the current will increase and then the voltage will increase, and if you do it in the same ratio, then you won't get any difference in time, which is actually what we want. But in this case, we'll just use the CTET voltage for the minus input of the comparator that we see here. And what we're going to do is you're going to reset a capacitor, and you're going to feed that PTET current into the capacitor. And as you know from the equations for a capacitor, well, I equals C dV dt, which means that if I is constant and C is constant, then the dV dt is constant. And since we know dV, because it's going to be your CTET voltage, then you can calculate what dt is going to be. And dt is basically the time it takes from 0 all the way up to the comparator flips, plus, of course, the delay of the comparator. Now, the circuit here, that basically just delays the comparator output for a certain duration in order to reset the capacitor. And that sort of starts, it goes up like a ramp, goes down again, up, down, generating a pulse that we can feed into a flip-flop and then generate a frequency out. This is typically called a relaxation oscillator. There are many ways to design these, and you're free to do what you want. The third milestone will be measuring. So now we have a frequency, but then we actually need to figure out what that frequency is. And that's where we can use a digital system. You're going to use Verilog, system Verilog, to design a digital system that would measure the frequency. And you can do this in a multitude of ways. You can either simulate together with your relaxation oscillator, or you can make a Verilog model of your relaxation oscillator and then simulate it together with a digital section where you have a finite state machine, something like what we're seeing here. For example, you have a idle state where you're resetting the counter. You're starting on some signal, and then we're powering up the oscillator. We run it for a single cycle, for example, or you can run it for multi-cycles. That's up to you. Actually, I'd prefer to run it on single cycle because that's going to be the lowest energy. We power down the oscillator, and then we figure out what the counter value was, and then somehow you have to turn that counter value into a temperature in order to figure out how accurate is my temperature sensor. Once everything works on the schematics and we have the Verilog system, we'll move on to Milestone 4, and this is, as I said, it's optional, but it is actually impossible to get an A on the project without having some points from the layout. So if you get the layout all the way to the end, you'll have a passing GDS LVS DRC action on GitHub. And let me show you what that means. So if we go back to, did I put the link in here? Yes, I did. Good. So I go here, and let's find the Genway again. And then I can just pick group 6. We can have a look at the layout. Let's see if that still works. Yes. So this is the layout of group 6. And once you have that layout, then you're also able to run the GitHub actions that we can see here. GDS, DRC. That's maybe a bit small. Let me make it bigger. GDS, DRC, LVS, and so on. And those are actually actions that run on the GitHub server that confirms that your layout is okay. And so layout LVS basically means layout versus schematics. So here you can also see the schematics for the temperature sensor. So this is previous years. Now, you can have a look at what they did last year. This one wasn't a relaxation oscillator. It was similar. It just did one reset. But I would recommend that you, instead of just blindly copying somebody else's work, you think for a bit and you try to make it better. So that's milestone 4. Now, milestone 5 is writing the report. And I've written the description of what you should have in your report. It needs to be an IEEE template, so it should look like a paper. And you could actually, if you wanted to, you could submit it as a paper to a IEEE journal if you make a fantastic temperature sensor. You wouldn't have a chip though yet, so you wouldn't get into journal of solid state, but maybe. Once the chip comes back, you can write it and submit it there. That'd be cool. But pretty hard though, very hard. Then the 6th milestone is actually the tapeout. And this is where you'll submit your design to Tiny Tapeout. I'm assuming that the Sky 26B will be in June. That might change, I guess. And as I said, I've gotten Nordic Semiconductor to sponsor the tapeouts in 2026. And that was what I planned to do on the project introduction. I've also written on Analogicus. You can find the project. I'll put it in the notes, lecture notes. No, in the YouTube notes. You can read more about it, and there'll be links. I want you to know one thing, though, and that is that you're going to design a temperature sensor, and that is the project. I am trying to force you into a certain way of designing the temperature sensor through a bandgap, relaxation oscillator, and so on. The reason I do that is that you don't know yet how difficult this is, and you don't know how difficult other type of circuits are yet. And what has happened before is that people have gone down routes where they try to make sigma modulators, or they try to make more complex temperature sensors that would require hundreds of schematics, and they never get to the end. So what I've tried to do is constrain you towards a temperature sensor that is relatively good, that has actually been demonstrated to work. And you don't need to take my word for it, although in an example here, I have made an example of the temperature sensor that I want you to make, so you can have a look at that. You'll find a description of it, description of the digital, you'll find the code for it, you'll find the performance of it. Actually, right now, I'm still working on the performance, so let's not look at that from this, but you'll also find a description of the details and how it works. Here is what I mentioned on the diode voltage, how it is a function that depends on the bandgap of silicon, and then there's a temperature dependent component, which turns out to have a temperature dependence that is T times, times a constant minus 3 ln T. And then this constant that depends on a whole bunch of stuff, including the effective mass of electrons and holes, which then come from, actually, this B thing. It's not actually a common factor in equations. What I've done here is massage the equations a bit in order to take out the temperature dependence that exists in the density of states, so that all the temperature components are in here, and then this L thing is just constant. It's around 2.3-ish for the technology that we're using. It also has the estimate of the current that we get from the bandgap over temperature and so on. And you have the full schematic for the bandgap core. You have for the op-amp. You have for the oscillator, relaxation oscillator, the comparator, the capacitor that we charge, and so on. And you can simulate that if you want. So I've made an example. You can find that in the lecture notes for the project. But I also want you to know that it's not just me that have made, well, actually, yeah, there are others that have made temperature sensors that look like the one I've made. So if you go into the PDF, you find so this was the PDF, by the way, for the project notes. You can click that button and then get a PDF version of the notes. So here in, I think it was number 4, you can open that up, and this is a temperature sensor that is actually similar to the relaxation oscillator you looked at just now. It's slightly different, but it's an interesting way of generating temperature sensors, and in this case they've actually shown plus minus 1%. And that's with 3 sigma. Okay. Before we leave it, I want to have a look at this actual temperature sensor. What you're looking at now is, I use this as this is XSchem, by the way. This is the schematic editor that we'll use. And what you're looking at now is a test bench that I use in order to debug the temperature sensor. So for example, here I'm able to, it's almost impossible to see, but what I'm doing now is changing the corners. Maybe we can make it bigger. Can we make it bigger? Is it possible? No, I don't think it is. It doesn't have an option for making it bigger. Okay, anyway. So here is some test bench text that gets netlisted, and we can press the netlist button. We can simulate. It takes a little bit of time. Once the simulation is done, there we go. Then we can load the simulation results, and we can have a look here at the output. So what you're seeing now is the VC here, the pink one, if that's possible to read. The pink one, that is our voltage that comes from that band gap. So it's that, let's see, it's that VC. That's that one. And then we have the current up here. We can see that it's about 1 microamp. Maybe you can see that. Maybe I can zoom in. That's even better. So here we have a current of about 1 microamp, and then we're charging 2 capacitors. And we can see that here we have a constant of VDT. And then at some point when it gets close to the trip point here, a comparator switches. So that's what happens here. And it changes state. And then we're off to the races. We're doing another cycle on a different capacitor and so on. And in the end, we'll get a frequency out that is proportional to temperature. So for example, now, if I, yeah, you can see the pink ones here. That is showing a certain cadence. Actually, let's remove the other ones. The power up will keep, and we keep just the green one. Okay, so every single clock cycle here, that is one charging of that capacitor, and then we get a certain frequency. So right now we're running a typical frequency. If I change the, typical temperature, if I tend to change the temperature to high, then the frequency of this oscillator should go up. So we can see now, let's do a manual count. Actually, I want the pink one. The pink one was better because it is a better initial state. Actually, it's better if we do the oscillation frequency. Like that. Make it blue. Oh, that didn't work. Really? Why? There we go. That turned pink. Okay, so let's remove that reset signal. And then the oscillator, now it turned green. Okay, yeah, here we go. So you have 1, 2, 3, 4, 5, 6. Oh, I lost count now. Let's try again. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. Roughly 9 clock periods. And now I change the temperature to high. We can simulate again. And now we should see more than 9. And this is how the digital will do it, right? It'll just count the number of clock cycles on this oscillator. And if the demo effect doesn't kick in, well, we can immediately see that it's more. So here we have, let's see if we can do it now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so that's sort of the top level function on this temperature sensor. All these schematics are available on GitHub. I'll put the in the links below. You'll see where they are. Oh, I moved it. So going into this temperature sensor, we can see that we have, actually let's go all the way into the bandgap. Here we have that bandgap circuit. We have, instead of using diodes, we're actually using 2 bipolars. So one is the size of 1, the other one is the size of 8. We can zoom in a bit. You can see, 7. 7 to 0, that gives you 8 devices. And then we have our op amp. This is a current mirror op amp with some power down transistors. And what you're seeing on the right side here is a cascade voltage generation. I don't have bias current coming into this op amp. I must be honest, in order to keep it simple, I don't want the feedback loop, or I don't want the startup conditions of the bandgap to influence the current in my op amp. I want the op amp to just work. So the way I generate the bias current in the op amp is basically just taking the common mode here, which gives common mode minus the VGS of the input diff pair gives me a certain voltage here at VS, and the VS to VDD voltage will give me a certain voltage drop across this resistor, and that's going to give me a certain bias current. And then I'm cheating over here by leeching off a bit of that bias current, feeding it in, and using it to generate the cascade voltage. Because in the current mirror, in the bandgap, you can see I have a couple of source transistors and cascade transistors. So, as I said before, if the op-amp does what it's supposed to do, then the VD1 will be equal to VR1, and we'll have the difference between VD1 and VD2 across this resistor, and that turns out to be a PTAT voltage, which turns into a PTAT current, and that's what comes out here at roughly a microamp. Now the compensation of the capacitor up here, that's for compensation. That's just to make sure that the op-amp is stable. The circuit on the left side here is trying to make sure that the bandgap starts up under all conditions, because bandgaps do have a tendency, well, can not start if the current in the current mirror is 0. This diode connected transistor down here is just to ease the startup conditions, because if the current is too high when the system is swinging in, then the voltage at VR1 is usually a bit too high, and that can actually lead to the input differential pair, well, actually the source voltage in the diff pair of the op-amp. This voltage can go a bit too high, the current can go too low, and suddenly you're into a slow settling condition. So the diode connection here is just to make sure that the voltage across these two nodes, it's kept way below half a volt. So that's the bandgap, and that gives us the current and the voltage that comes out. So the voltage we feed into a comparator directly. The comparator is a simple two-stage op-amp. Nothing special there. It gets its bias current from the bandgap. And then the other bias current, there's two bias currents coming in. We can see that here. So one of them is fed to the capacitor, charging that voltage up until it reaches the level of the comparator. The comparator will flip. The comparator output is connected, just ignore this and, connected to this SR latch, which means that the state, the reset B and reset A here, will flip back and forth. So first it'll charge one, then it'll charge the other. And this way we don't need to take into account the time it takes to reset the capacitor, because we can actually have a quite small transistor on the reset here, and we can allow for quite a bit of time for the reset of the capacitor to the right voltage. Okay, so that's sort of the whole system. And then there will be Verilog code in this example. So you can go to the GitHub repo and actually let me show you that. So if I go projects, I find where I mentioned the temperature sensor. There we go. This brings to the documentation page, right? And you can read about the schematics, what I've just said, how this thing works. And you can read about the simulations. You can then also, actually, the easiest way is you can click this docs passing. That will bring you to the GitHub repo. Click here. Oh, there we go. It's a bit slow today. And this is all the files. So for example, in here you'll find the RTL. So here we have the counter. So this is a simple counter. Maybe it's a bit small. Let's try to make it bigger. Actually, I can open it up in the editor. So RTL, we have the counter. Can you see that? Yeah, let's make it even bigger. There we go. So here is the clock that comes in from our oscillator. It will be counted by just, well, here I'm using always comp and always FF to generate the counter of a certain width. So iCount is the internal count. This is made by combinatorics. So it takes the previous output value plus 1 and then shifts that in on the next pulse edge of the clock. To run this whole thing, there will be a finite state machine that is also described with the idle, power up, power down, capture, and so on, and how that runs. And then there will be in the simulation folder, there will be a test bench here, a Verilog test bench, in order to actually run the oscillator. Now, in this simulation, I'm not running the oscillator in SPICE. I've made a Verilog model of the oscillator because I know how the physics works. So it is entirely possible to write a Verilog model. So this is, so you can see that it has the power up, power VDD, VSS, oscillator temp, which is the temperature dependent oscillator frequency that comes out. And then I'm cheating a bit. I'm using defines to sort of insert a temperature into this model. Because once I know the temperature, then I can calculate the diode voltage from the equations that we know. Or not that you know, that I know. We can calculate this delta voltage. We can calculate, this is actually modeling the temperature dependence of the resistors, because it turns out that the Skywater RP polar resistors, they have a temperature coefficient. So they increase in resistance as the temperature goes up. And then we can calculate the current that comes out of the bandgap. And then we can calculate the dt, so the delta time, that it takes for the capacitor. So this is basically the I equals C dV dt equation. So we have dt equals the capacitor times the voltage that we're charging to, divided by the current, and then turning it into nanoseconds. And I'm adding also here a factor for the comparator delay. And then we're switching the clock. So here it's actually a digital model of the analog oscillator. And that I can insert into my test bench. So let's see, here we have that design. And then I'm instantiating my counter and my FSM. I have also tried to run the real oscillator, the SPICE oscillator, together with these two digital circuits. But I've struggled a bit because it turns out that it doesn't seem like Verilator likes multiple different clocks. And what we have here is a situation of clocks that are asynchronous to each other. So you can see that the counter, that actually runs on the oscillator clock that comes out from the analog, while the state machine, that runs on the low frequency clock, which is the 32 kilohertz clock. And I haven't been able yet to get all that into the same SPICE simulation. But let me just show you how this works. So if we go to sim tb lilo temp, there will be a make file, as always. And well, what happened now was it ran through, and let's open up the test bench so you can see that. It ran through the temperatures and then used the counters to figure out what the count was, and then back propagate back to temperature and so on. So here we can see the test bench. You can actually, is it big enough? So we're resetting the oscillator. We are starting the oscillator. We're starting the final state machine. And then for temperatures from -40 to 125, when the FSM says that it's done, then we'll do another cycle and change the temperature, read out what the new oscillator count is. This is, of course, a very fictitious way to do it, but it's a good way to check that the physics is correct. And it's a good way to also design the digital code, because I don't have to run the SPICE simulation. This is an incredibly quick simulation. So if we open up Surfer here, and what do we need? We need probably start. We need done. And what else do we need? Cycles. Yes, and I think there is a way to zoom in. Yes, there is. No, that's not it. I want zoom factor. There we go. So we can actually make it a bit bigger here. Okay. And then if I do that, we should be able to get to a start cycle. So what we can see here is the finite state machine starts. Oh, we need reset. And then it resets. Reset count? No, that's not it. FSM. Reset. Yeah, okay. Yeah, it was. Yeah, so we can see that the count is reset. The reset is released. We need the power up signal. Where's that? Power up oscillator. So here we power up the oscillator. And then we can see that the oscillator is powered up. It counts at a relatively high frequency. And we can see that the count value is increasing. And then after one clock cycle, which we probably should also have in here, this is the clock cycles. After a clock cycle, we power down the oscillator, and then in the next rising edge of the clock, we can read out what the oscillator counted to. Now, that is in the test bench stored to a file, and then we can use a Python program in order to translate it back into temperature. Because that's the cool thing, right? We know how this works now. We know the physics of it. So I can have my Python model of my circuit. And where should I start? Yeah, so I get the frequency from the oscillator. And I can divide that by 2 because the DT factor, that's for every single, well, there's 2 of those time periods in a full period of the oscillator. I can subtract the comparator delay, just roughly know what that is. I can calculate back what the current should be because I know what the C should be. Now C here will change with process though. So that's going to be modified. And also the VC, which is the diode voltage, that is also going to change with process. So this is not going to be entirely correct. But I can calculate what the current was. And for the, here it's a bit of a trick though, because the VC, that's actually temperature dependent, right? Because we looked at those equations. So to calculate that, that was this KT divided by Q times T times this constant factor minus 3 log of the temperature in Kelvin. But we don't know what the temperature is because that's what we're trying to figure out. So in this case, what I'm actually doing is just saying, okay, let's just pick the VC at the center point, which is 42 degrees because that's the center between minus 40 and plus 125. So that's going to introduce an error into our current here. And then we can calculate this delta voltage from the current and the resistor. Now the resistor will also have process variation, plus minus 10-20%. Same with the current with the capacitor. And then we can get to the actual temperature. So what we actually know now is that the temperature we get out is going to be wrong because we don't know what the temperature is. So we can't calculate the correct R. And we can't calculate the correct diode voltage. And we don't know what the process is, so we don't know exactly what type of C we have or R we have. But it turns out that most of those factors, they will either turn into an offset or they turn into a gain error. In some cases, they actually turn into nonlinearity. But what we can do for typical devices is actually to run a compensation function. Because since I actually know the physics of how this oscillator should work, then I can just generate a temperature range. I can calculate what the frequency was, or should be, what the oscillator frequency should be, and then I can back calculate what an estimated temperature could be if I didn't know what the temperature was. And then I can make a second order polynomial to go from the estimated temperature to the probable true temperature. Now, of course, all this stuff is a bit tricky to do in digital, maybe. So you'd have to simplify, you'd have to modify. In a microcontroller, it might not be that tricky. But my point here is that since we know how the physics works and how the equations works, we can actually figure out how the output of the temperature sensor can be mapped back into actual temperature. So when we now look at a real simulation, let's find a terminal. Was that a terminal here? There we go. So if I go to the SPICE simulation, did I need to run it? By the way, I'm running 2 simulations now because I'm actually doing a 2-point calibration in my design, or calculating what a 2-point calibration would entail. Okay, so here I have a SPICE simulation that is running at 25C and 85C, and based on that I have a from that I have a Python script that runs, that figures out what is the 1-point offset needed, and 2-point offset and 2-point gain in order to calibrate the function. So that's what actually came out here in the previous log. You can actually see that it's pretty close. The 1-point offset is only 0.24 degrees. So when I now have run the temperature sensor over multiple different temperatures, I can plot those, and then we can see the temperature error. And we can see here that for a typical condition, 1 point, we can see that the temperature error stays within, well, plus minus a degree or something for typical conditions. But over corners, this will vary a lot more. So there is an example of a temperature sensor. And if you didn't understand half of what I said right now, that's fine. That is fine. You will understand more once we're finished, and we're going to take it one step at a time. So I hope that you will get all the way to the end. I look forward to see your designs. I look forward to discussing temperature sensors with you, and this should be fun. Now, if you're out in the wild world and you also want to do the project, feel free. And if you want to ask me questions, feel free. I might respond. Thank you and have a fantastic day.